Physicists have so far discovered 25 elementary particles that, for all we currently know, aren't made up of anything else. Most of those particles are unstable and they'll decay to lighter particles within fractions of a second. But how can it possibly be that a particle which decays is elementary? If it decays, doesn't this mean it was made up of something else? And why do particles decay in the first place? At the end of this video, you'll know the answers. The standard model of particle physics contains 25 particles, but the matter around us is almost entirely made up of only half of them. First, there's the electron. Then there are the constituents of atomic nuclei, the neutrons and protons, which are made up of different combinations of up and down quarks. That's 3. And those particles are held together by photons and the 8 gluons of the strong nuclear force. So that's 12. What's with the other particles? Let's take, for example, the tau. The tau is very similar to the electron, except it's heavier by about a factor of 4,000. It's unstable and has a lifetime of only 3 times 10 to the minus 13 seconds. It then decays, for example, into an electron, a tau neutrino, and an electron antineutrino. So the tau may be just made up of those 3 particles, and when it decays they just fly apart. But no, the tau is not made up of anything, at least not according to all the observations that we currently have. There are several reasons physicists know this. First, if the tau was made up of those other particles, you'd have to find a way to hold them together. This would require a new force. But we have no evidence for such a force. For more about this, check out my video about fifth forces. Second, even if you'd come up with a new force, that wouldn't help you, because the tau can decay in many different ways. Instead of decaying into an electron, a tau neutrino, and an electron antineutrino, it could, for example, decay into a muon, a tau neutrino, and a muon antineutrino. Or it could decay into a tau neutrino and a pion. The pion is made up of 2 quarks. Or it could decay into a tau neutrino and a rho. The rho is also made up of 2 quarks, but different ones than the pion. And there are many other possible decay channels for the tau. So if you'd want the tau to be made up of the particles it decays into, at the very least there'd have to be different tau particles, depending on what they're made up of. But we know that this can't be. The taus are exactly identical. We know this because if they weren't, they'd themselves be produced in larger numbers in particle collisions than we observe. The idea that there are different versions of taus is therefore just incompatible with observation. This, by the way, is also why elementary particles can't be conscious. It's because we know they do not have internal states. Elementary particles are called elementary because they are simple. The only way you can assign any additional property to them, call that property consciousness or whatever you like, is to make that property entirely featureless and unobservable. This is why panpsychism, which assigns consciousness to everything, including elementary particles, is either bluntly wrong, that's if the consciousness of elementary particles is actually observable because, well, we don't observe it, or entirely useless, because if that thing you call consciousness isn't observable, it doesn't explain anything. But back to the question why elementary particles can decay. A decay is really just a type of interaction. This also means that all these decays in principle can happen in different orders. Let's stick with the tau because you've already made friends with it. That the tau can decay into the 2 neutrinos and an electron just means that those 4 particles interact. They actually interact through another particle, which is one of the vector bosons of the weak interaction, but this isn't so important. Important is that this interaction could happen in other orders. If an electron with high enough energy runs into a tau neutrino, that could, for example, produce a tau and an electron neutrino. In that case, what would you think any of those particles are made of? This idea just doesn't make any sense if you look at all the processes that we know of that taus are involved in. Everything that I just told you about the tau works similarly for all the other unstable particles in the Standard Model. So the brief answer to the question why elementary particles can decay is that decay doesn't mean the decay products must have been in the original particle. A decay is just a particular type of interaction, and we've no observations that it indicate elementary particles are made up of something else. They have no substructure. That's why we call them elementary. But this brings up another question. Why do those particles decay to begin with? I often come across the explanation that they do this to reach a state of lowest energy, because the decay products are lighter than the original. But that doesn't make any sense, because energy is conserved in the decay. Indeed, the reason those particles decay has nothing to do with energy. It has all to do with entropy. Heavy particles decay simply because they can, and because that's likely to happen. As Einstein told us, mass is a type of energy. Yes, that guy again. So a heavy particle can decay into several lighter particles because it has enough energy, and the rest of the energy that doesn't go into the masses of the new particles goes into the kinetic energy of the new particles. But for the opposite process to happen, those light particles would have to meet in the right spot with a sufficiently high energy. This is possible, but it's very unlikely to happen coincidentally. It would be a spontaneous increase of order, so it would be an entropy decrease. That's why we don't normally see it happening, just like we don't normally see eggs unbreak. To sum it up, decay is likely, undecay unlikely. It's worth emphasizing, though, that the reverse of all those particle decay processes indeed exists, and it can happen in principle. Mathematically, you can reverse all those processes, which means the laws of nature are time reversible. Like a movie, you can run them forwards and backwards. It's just that some of those processes are very unlikely to occur in the world we actually inhabit, which is why we experience our life with a clear forward direction of time that points towards more wrinkles. This video was sponsored by Brilliant, which is a website and app that offers interactive courses on a large variety of topics in science and mathematics. When you wonder why the world is how it is, it's amazing how often the answer comes down to statistics and probability. If there was one topic I'd have to single out that will help you to make sense of everything, that'd be it: statistics and probability. And Brilliant is a great way to learn more about this or to freshen up your knowledge. To get some background on this video, I'd recommend, for example, you check out their courses on probability fundamentals, statistics, and knowledge and uncertainty. All their courses challenge you with questions so you can check your understanding along the way. To support this channel and learn more about Brilliant, go to brilliant.org/Sabine and sign up for free. The first 200 subscribers using this link will get 20% off the annual premium subscription. Don't forget to subscribe and like this video if you enjoyed it. It's free, it's simple, and it really helps us find sponsors. Thanks for watching. See you next week.